Hey math friends, welcome. This is AP Calculus section 3.3, day 1 and 2 notes combined together. So today we are going to talk about rates of change in the natural and social sciences, which basically means we're going to pause our new learning and kind of reflect on what we know right now about derivatives and how they can be applied to real life situations. Those of you that are taking AP Physics, you are going to find this section has so much in common with some of the content that you've covered in your AP Physics class. There's a great amount of overlap between AP Calculus and AP Physics, and today is one of those days where you are going to see a ton of it. So our whole notes today is just one problem with a whole lot of parts to it. Our one and only example 1 says, the position of a particle is given by the equation S, which is f of t, it's a function in terms of time, is equal to t cubed minus 9t squared plus 15t for values of t between 0 and 8, where t is measured in seconds and S is measured in meters. So since this given equation is S, that tells us that our initial function that we are given here is a function for position of this particle. So let's write that down. So this is position. All right, so part A asks us to find the velocity at time t. Well, we know from our previous work that velocity is the first derivative of position. So basically, v of t is going to be equal to f prime of t. We used to have to do the difference quotient to find this derivative, but now that we know the power rule for polynomials, finding the function for velocity is just a walk in the park. The derivative of t cubed is going to be 3t squared. The derivative of negative 9t squared, bring down the 2. Negative 9 times 2 is negative 18, and that becomes t to the first. And the derivative of 15t is 15. So right here, v of t is equal to 3t squared minus 18t plus 15. Part B then asks us to apply our new velocity function by asking us what is the velocity after 2 seconds, after 4 seconds, or after 6 seconds. So we need to find v of 2, which is going to be 3 times 2 squared minus 18 times 2 plus 15. Grab your calculator. You should get a velocity of negative 9 meters per second. Why is the velocity negative? Because the particle is moving in the backwards direction at this point in time. V of 4 is going to be 3 times 4 squared minus 18 times 4 plus 15. You do the math and you get again negative 9 meters per second. So same velocity after 4 seconds as after 2 seconds. The particle's still moving in the negative direction at that point in time. And then finally, v of 6 would be 3 times 6 squared minus 18 times 6 plus 15, which gives me a velocity of positive 15 meters per second. So now the particle, after 6 seconds, is moving in the positive direction at 15 meters per second. Part C asks us, when is the particle at rest? Okay, well, important note. Particle is at rest. At rest means not moving, right? So the particle is at rest when our velocity, v of t, is equal to 0. So let's set our velocity function equal to 0. So 0 is equal to 3t squared minus 18t plus 15. I can factor out a GCF of 3. And then I have t squared minus 6t plus 5. And now that's just an easy factor. That's going to be 3 times t minus 5 times t minus 1, which when I use the zero product property tells me that the particle is at rest at time t equals 5 seconds and at time t equals 1 second. Part D asks, when is the particle moving forward or in the positive direction, and when is it moving backwards? Well, we already talked about how when the velocity is positive, the particle is moving forward, and when the velocity is negative, the particle is moving backward. So let's start with forward motion. Particle is moving forward when our velocity is positive. So when v of t is greater than 0. Well, I already have v of t in factored form, so I'm going to go ahead and grab that. V of t is 3 times t minus 5 times t minus 1, and I want to know when is that greater than 0. So once again, we're talking about sign charting here. And if we want greater than 0, we want to know when this inequality is positive. My critical values are obviously going to be 1 and 5. And so I am looking at first numbers that are a number that is less than 1. How about 0? When I plug 0 in, I'm going to get 3, which is a positive, times 0 minus 5 is negative 5, so that's a negative. And 0 minus 1 is a negative. Well, a positive times a negative makes any values less than 1 come out to be positive in our velocity inequality. If I plug a number in between 1 and 5, how about 2? I'm going to get positive 3. Sorry about that. Oh my goodness. I'm going to get positive 3 times 2 minus 5 would be a negative, but 2 minus 1 would be a positive. Positive times positive makes this region negative. And then finally, if we plug something bigger than 5 in, how about 6? We're going to get positive 3 times positive 1 times positive 5. Positive makes positive. So I have 2 regions here where my velocity is positive. So I can safely say that the particle is moving forward when t is less than 1 second or when t is greater than 5 seconds. All right, so now when is our particle moving backward? Well, as you can guess, it's moving backward when v of t is less than 0. And we've already done our sign charting for 3 times t minus 5 times t minus 1 is less than 0. Same exact sign chart with 1 and 5, except now we are interested in where our values are less than 0, and we know that that happens between 1 second and 5 seconds. So our answer here is particle is moving backwards when 1 second is less than t, which is less than 5 seconds. Letter E asks us to draw a diagram to represent the motion of the particle. You are going to find this to be a very strange looking diagram. And I'm not going to ask you to do this on a quiz or a test, don't worry. This line right here represents S, which is the position of the particle. So we are trying to graph the fact that this particle is moving both in the positive direction and in the negative direction. So the movement of the particle, we know that the particle starts at time t equals 0. And it's moving in the forward direction for a little while. And then it turns around at time t equals 1 second. Because from t equals 1 second to t equals 5 seconds, the particle is moving in the backwards direction. And then at t equals 5, it turns around again, and it starts moving in the forward direction from that point forward. So we're just going to draw some little arrows here to show the direction in which the particle is moving at any given time. Letter F asks us to find the total distance traveled by the particle during the first 8 seconds. Okay, this is perhaps the trickiest part of this problem. Because the particle is moving both forward and backward, we need to calculate forward and backward distance separately. And then find the sum. Of the absolute values of the distances. All right, because we know that our particle is moving forward on the time interval 0 seconds to 1 second. Then we know that our particle is moving backwards on the time interval 1 second to 5 seconds. And then we know that it turns around again and it's moving forward from 5 seconds to 8 seconds. And we're supposed to do the first 8 seconds. So how do we find how far the particle is gone? Well, if we knew the position the particle started at and we knew the position the particle ended at, we could just subtract those two, and that would be the distance that the particle moved over that period of time. Well, lucky for us, we have a position function, right? The original function that was given in the problem, f of t, is a function for the particle's position. So basically, we could do the absolute value of our ending point, which would be f of 1, minus our starting point, which would be f of 0. So if you grab your calculator and you plug 1 in to the f of t function, you get 7 meters. And if you plug 0 in, you get 0 meters, right? So that tells us that in the first second of this particle's traveling, it traveled a total of 7 meters. Then from 1 second to 5 seconds, we're going to do the same thing. We're going to take the absolute value of our difference here, but we're going to find first, where did the particle end up after 5 seconds, f of 5, and where was the particle after 1 second? We know that it was moving in the backwards direction at this period in time, so we know that this is going to be negative, but when we take the absolute value, it will come out positive. Well, when we plug 5 into our position function, f of 5 gives us a distance of negative 25 meters, minus, and f of 1 we already knew was 7 meters. So negative 25 minus 7, that's negative 32. Absolute value of negative 32 gives us 32 meters in the backwards direction. But again, absolute value is positive because we're looking for total distance traveled here, so all positives. And then finally, from 5 to 8, we have to do f of 8 minus f of 5, which f of 8 is 56, and f of 5 is negative 25. So 56 minus negative 25, because we started in the negatives and then we went positive back to 0 and then positive some more. So 56 minus negative 25, absolute value of that is 81 meters. So now to answer the question, we just have to add 7 plus 32 plus 81, which gives us a grand total of 120 meters. Is the distance that the particle traveled during its first 8 seconds. Letter G asks us to find the acceleration at time t. Well, think back to the relationship that we know about position, velocity, and acceleration. Acceleration is the derivative of velocity and is the second derivative of position. Well, we already have our velocity function, so we know that our acceleration function is going to be equal to the derivative of our velocity function. Again, velocity was 3t squared minus 18t plus 15. So the derivative of 3t squared, bring down the 2, multiply it times the 3, that's going to be 6t. And the derivative of negative 18t is just negative 18. The derivative of 15 is a constant, it goes to 0. So our acceleration function is 6t minus 18. Whoops, sorry about that. Now we can use our acceleration function to answer part H, which asks us to find acceleration after 2 seconds, after 4 seconds, and after 6 seconds. So A of 2 is going to be 6 times 2 minus 18. 12 minus 18 is negative 6. Units on acceleration are meters per second squared. A of 4 is going to be 6 times 4 minus 18. 24 minus 18 gives us positive 6 meters per second squared. And then finally, A of 6 is equal to 6 times 6 minus 18. 36 minus 18 gives us positive 18 meters per second squared. Letter I asks us to graph the position, the velocity, and the acceleration functions for 0 to 8 seconds. So we're going to start by making a coordinate plane here, and you might want to color code this because we're going to be graphing 3 different functions on the same coordinate plane. Eight seconds there on our x-axis. This is time in seconds. And then I'm going to count by 5s on my y-axis. It's going to be 5, 10, 15. All right, so if you want to at this point, you can certainly grab your graphing calculator and you can take a look at what the graphs look like on there, and I encourage you to do so. But I have already taken the time to do all 3 of these graphs, and so I am just going to start by saying that f of t, which is my position function, which I know is t cubed minus 9t squared plus 15t, obviously is going to be a cubic polynomial. It has an intersection point here at 0. There's another x-intercept that's a little bit more than 2, and there's another x-intercept at just a little before 7. So like right here. It has a local max, which is kind of right here between 5 and 10, and it has a local min when t equals 5 seconds, and it's down here about negative 25. All right, so this is what our position function looks like. And again, you can certainly verify that if you grab your calculator and you take a look at your graphing calculator. Okay? Then the next function we have is our velocity function. So let's change colors here. V of t, our velocity is equal to 3t squared minus 18t plus 15. And that looks like a parabola. We already solved for the x-intercepts of that one because we wanted to know when velocity was 0. So it's got x-intercepts at 1 and at 5. And it has its local minimum at about 3, negative 12 or so. So like right there. And so our velocity looks like this. And then finally, we have our acceleration, and we know that our acceleration is a linear function, or a y equals mx plus b equation. A of t is equal to 6t minus 18. So y-intercept of negative 18, and it has an x-intercept at 3 right here. So our acceleration function looks something like that. All right, so we've successfully graphed our position, velocity, and acceleration functions on the same graph. And so then letter J is going to ask us to answer the question. Moving on to letter J. When is the particle speeding up and when is the particle slowing down? Okay, so let's write some information down here. The particle is speeding up. Sorry about all those pop-ups there. My daughter's messenger. The particle is speeding up when v of t, velocity, and a of t, acceleration, have the same sign, meaning they are both positive or both negative. Oops. Okay, because the particle is pushed in the same direction it is moving. Okay, and so then, kind of opposite of that, the particle is slowing down, and I left some space there on purpose, so leave some space. The particle is slowing down when velocity and acceleration have opposite signs, meaning one is positive and one is negative. And this is because the particle is pushed in the opposite direction from which it is moving. So in order to answer these questions, the easiest thing to do would be to take a look at the beautiful graph that we just made. So if we go back and we look at our paper, we want to know, for the particle to be speeding up, the velocity and the acceleration have to have the same sign. So they have to either both be positive or both be negative. So we're focusing right now on the purple graph and the green graph. So where are they? Let's see. Well, when the graph begins, velocity is greater than 0, and acceleration is less than 0. Okay, so from 0 to 1 second, they have opposite signs. But then they're both negative for a while, right? They are both negative until, let's see, until right here, when the green graph goes above, and then they have opposite signs for a bit again, right? Then they have opposite signs until about right there, and then once the purple graph goes above the x-axis, then they have the same sign again. So there's kind of a color-coded explanation of when the particle is speeding up and when the particle is slowing down. The velocity and acceleration have the same sign between t equals And again, I'm looking along the x-axis here. So between t equals 1 second and t equals 3 seconds, they're both negative. And from t equals 5 seconds on, they're both positive. But from 0 to 1 second and from 3 to 5 seconds, they have opposite signs. So they're going to be, or the particle is going to be slowing down. So let's put an answer on our question here. The particle is speeding up when t is between 1 and 3 seconds and when t is greater than 5 seconds. And the particle is slowing down when t is between 0 and 1 second and when t is between 3 and 5 seconds.